Hi, my name is Itamar, and today I'm going to be talking about vectorization, how slow Python runs fast code. And Python has a bit of a paradox when it comes to performance, to running software quickly. On one hand, Python is slow. And when I say Python, mostly I'm talking about the default Python interpreter, also known as CPython. Since it's the one almost everyone uses, I'm just going to use them interchangeably, but there are other implementations of Python. But most of the time, for most versions, Python is pretty slow. And Python is also a popular language for scientific computing, data science, and so on. And data processing often involves lots of data. And processing large amounts of data takes time, and you don't want to wait longer than you need to, so you want your software to be fast. So how do you get fast results from a slow language? How did Python become so popular for data processing? It's easy to use, it has a lot of libraries, but being fast enough to be usable is a minimal requirement. So how did that happen given Python is so slow? And the solution that people have come up with is known as vectorization. And it's going to be a topic of the talk today. And the general idea is you can implement general purpose operations on arrays in a faster language. Arrays might be two-dimensional, one-dimensional. Quite a lot of data can be represented as an array, numeric array. You expose these generic operations, like a sum, a mean, and so on, in libraries, NumPy, SciPy, Pandas. And then insofar as you can then use regular Python code to assemble these generic fast functions into more specialized algorithms. And to see why we might want to do this, it's worth looking at an example. So let's say we have a NumPy array. We have some large number of integers or floats, and we want to calculate the mean, the average. And so here are two different ways to do it. In one, we're just going to use pure Python, and we'll do it a little bit like you would in a lower level language, looking up things by index. So we initialize total, we iterate over values from 0 to the length of the array, we add up each individual item in the array in total, and then we divide the total by the length of the array. Now we have the mean of the array. And the other way we can do that is using NumPy's sum function, which is a vectorized function. And we'll talk about what vectorized means specifically as we go on through the talk. But we have this function that will sum an array for us, and we divide that resulting total by the length of the array. So in terms of correctness, you don't really care which version of these you're using. Right? You could use one, you can use the other, you're going to get the exact same results. So either way, it really doesn't matter. But what does make a difference is when you care about speed. So semantically, you don't care. But if you run this on some array that has 30 million integers, I generated them randomly, yours hopefully has more meaning. If you use a Python for loop, it takes 2 seconds. If you use a vectorized numpy.sum function, it takes 20 milliseconds. So that's 100 times faster. And so you can imagine with 100 times speed up, you might be going for a more significant calculation. You might go from something taking an hour and a half to only taking 1 minute. And if something takes an hour and a half, there's only so many experiments you can do in a day. If something takes a minute, you can do far, far more attempts to improve your software. You can give results to your users much faster. It's just much, much better. And this is really an extremely useful improvement in speed. And sometimes it's only 20 times or 50 times faster, but it's all the same in terms of getting these order of magnitude improvements is a huge benefit in terms of being able to develop your software faster, give results faster to your users, reduce your compute costs, and as a nice side effect, reduce your carbon emissions if you're operating off electricity that isn't sustainably produced. So for the rest of this talk, we're going to dive into the problem, the solution, which is vectorization, and we'll define it in a much more accurate way. There are multiple definitions and they matter. And then we'll talk about some practical implications, how you can learn what you've used to write faster code using vectorization. And we'll start by talking about why Python, again, this is the default Python implementation, why Python is slow. So imagine you're iterating over a range object. You want to do 0, 1, 2, 3, 4, 5, and so on. This is a quite common thing to do, especially when you're dealing with arrays of data. You might want to look things up at different indices. So every iteration, every single one of those numbers gets returned. Python will call a function to get the next value. And here's the C code for Python interpreter implementation. And so it's checking if we hit the end of the range object. It's calling a function called pylong from long, and it's passing in some arguments. So this is doing a little bit of work. It's not in this particular function. It's not doing that much work, but it is more work than, for example, doing a for loop in C or some other low-level language, but it's still not too bad until we look into this function pylong from long. That's going to be called on every time we go through the iteration. If we iterate over 1 million values, that function is going to be called 1 million times. This is what the function looks like. And I've used a smaller font because it's quite long and you don't really have to understand what it's doing. The main point here is that it's doing a decent amount of work, and if you pay attention, it's actually calling other functions along the way. And so what's going on here is that when we are getting these series of numbers, 0, 1, 2, 3, 4, we're using Python's implemented in C, so it's running some C code to get those numbers. But Python, the interpreter, when it creates an object that you interact with from Python, doesn't use C integers. It uses Python integers, known as pylong objects. And they're a much more complicated object than what the CPU is using, than what C is using. And so you have to convert from the C integer, a long, into a Python integer, a pylong object. And doing that conversion is fairly complicated. And so that means just iterating is going to be slow because we're doing this fast operation of doing a sequence of numbers, and then we're creating a whole bunch of Python objects. And creating Python objects is expensive. It has to do a lot of work. It has to convert the data from one format to another. You might have to do some allocations. It's not just creating Python objects. Python integers takes a lot of work. Another thing we might want to do in Python is some math. Let's say we want to add 2 integers. So if you dig into the implementation of the interpreter, this is the entry point function that adds 2 integers together. There's actually some work that happens even just to get to this point, but we'll just ignore that. So again, this is a fairly complicated function that's calling other functions. And the reason is, in order to add 2 numbers together, you need to have something that the CPU understands is a number. And what Python has is a pylong object, which is Python's interpretation of a number. And so you have to convert from a pylong object into something the CPU understands. And that takes work. And so now we're seeing the work in the opposite direction. Previously, we were turning a C integer into a Python object. Now we're turning a Python object into a C integer. And in order to do any math, we have to do these conversions, and that just adds a lot of overhead. Another reason that Python is slow is the way it represents objects in memory. And we're talking about numeric data here. We're talking about arrays. So we think about a C array or a fortune array. The CPU knows about 64-bit integers. And in order to have an array, we just put these 64-bit integers, which are 8 bytes each, one after each other in memory. So the number 1, 2, 3 is 8 bytes, and then right after it, we have another number, 4, 5, 6, another 8 bytes. And so to iterate over these values, we just skip ahead 8 bytes at a time, read 8 bytes, and then we call CPU instructions. If you want to sum these, it's very, very fast because it's just jump ahead 8 bytes, call one CPU instruction to sum these 2 numbers, continue. So this whole memory layout is designed to match the way the CPU thinks of data. It's designed to be fast. If we move to Python, however, things get more complicated. If we have a Python list of integers, it is actually an array, and that's fine, that's fast. But it's an array not of integers, it's an array of Python objects, generic Python objects. Because you can imagine you can have a list that's an integer and then a string. Python doesn't really know. And so each of those pi objects is a pointer to some other location in memory. So first we're going somewhere else in memory, which also takes a little bit of time. And then we have over there another object, which luckily is a pi long object. It isn't Python integer. That's 28 bytes. And then we have to, as you remember, recall, convert that back into something that the CPU can deal with. And so doing something with a Python list of integers involves quite a lot of work of calling Python APIs to look up objects, to convert objects, a lot more memory reads and writes, which can be very expensive once you're using enough data. And it also uses more memory, just as a side effect. In short, Python is slow in large part because it's converting in between Python's in-memory object representation and into machine representation and back. And interacting with Python objects, including lists, involves lots of Python APIs. And Python does all this because it wants to make your life easier. It might like to make things just more flexible. And so you get all these benefits of the Python language from these representations, but you also get the downsides of all these interactions being slow. So Python is slow. We'd like to make things fast. And specifically, we want to make things fast for numeric arrays, which are one of the most commonly used data structures if you're doing data processing, scientific computing, the like. And the basic idea is that you take a C array, which we saw is nice and efficient, of a specific type, for example, a 64-bit integer. We make a wrapper around it, a Python object that wraps around that C array. So it's just a C array. It's just a low-level array that allows you to do fast operations. And it's just hiding inside a Python trench code. But underneath the hood, it doesn't really have anything Python specific. And because of that, you can completely bypass all of the Python APIs, Python objects. You don't have to worry about Python integers. If you want to sum this array, from your perspective, it's just some code that is summing a C array, which we can do quickly. And then you can do all your fast operations. And then when you're done, you can convert it something back into a Python object maybe. But it's only the beginning at the end that you know about Python. In between, everything is running really quickly. Pandas data frames are implemented underneath the hood using NumPy arrays. There are other Python libraries like NumPy that are slightly different. In the end, the model they use underneath is the same one of a C array that is just a thinly wrapped by Python. And in this context, vector is just a synonym for array, and that's where the word vectorization comes from. So just to go into more detail about why this is useful, let's say we have a million integers and we want to sum them. So if we are doing this with a Python list of Python integers, we're going to have to read those list items one by one and actually make sure they're integers. And just reading items in a list requires calls in the Python C API. So we're calling these Python C APIs a million times. And then we get back all these Pylong objects, and those Pylong objects aren't something the CPU can add. So we have to do all this work to convert those Pylong objects into something the CPU can actually add. And after all that overhead, then we can finally do some math. So before we get to the math, there's just a huge amount of interacting with Python objects. It really isn't helping us get our answer. It's just work. It's wasted work. On the other hand, we can add up a million integers that are in a NumPy array using NumPy's sum function. And the NumPy sum function will say, okay, you're a Python object, but inside of you, you're just a C array that's hiding. And now I have a C array, and adding numbers in a C array is really quite fast. Like you just jump ahead a few bytes at a time. It's adding each pair of integers is just like one CPU instruction. And then all the way at the end, you have a sum. And then maybe you turn that into a Python object, but then you're just doing one conversion into a Python object instead of millions. And so there's just much less overhead. It's much faster. Now, one thing to keep in mind that just because you're operating on a whole array, or even just because your code is written in a low-level language, doesn't mean it's going to be fast. It might still be slow. So we were talking about NumPy's sum function, but Python also has its own built-in sum function. And we can call it with NumPy array, and it will still be slow. It's implemented in a fast language. It's operating a NumPy array, but it's still slow. So why is that? And the reason is that it's calling back into Python on every item. Python's built-in sum is designed to work on generic Python objects. You can pass in a NumPy array, but you can also pass in a Python list. You can pass in a Python iterator. And so from its perspective, it is taking a sequence of Python objects and it is summing them, which means every item requires you to do stuff with Python APIs. And it has some specialized code paths for integers, but that's not enough to override the fact that you still are calling into Python APIs like pylong as long and overflow, and pysize and pylong check exact, and so on and so forth on every single item in the object you passed in. Whether or not it's a NumPy array or a Python list, it doesn't matter. Python's built-in sum function is calling into C Python APIs over and over and over again. And the result is that it is still quite slow. So if you use a Python for loop to sum up 30,000 million random integers that are in a NumPy array, Python's built-in sum is a little bit faster than the for loop, but NumPy's sum function is where you get the benefit of 30 times, 50 time improvement in runtime because you're actually able to bypass Python altogether. And that leads us to a definition of a vectorized API. And there are two meanings for a vectorized API for our purposes. And differentiating between these is important because, as we've seen, sometimes a thing might look like it'll be fast, but it isn't. A vectorized API might be a bulk API, a function that operates on a whole array. And if it's a bulk API, it might also additionally be a fast API. That is an API that is implemented in a fast language like C or Rust and does not call back into Python APIs per item. And the first meaning, being a bulk API, is a prerequisite for the second meaning. There's also a third meaning, something called SIMD, which is jargon in low-level programming like C. I'm not going to go into today because of lack of time, but just if you're talking to a low-level programmer and they talk about vectorization, be aware they might be talking about something rather different, related but different. So just as a side note. So if you look through think about the three ways we've implemented summing of an array of integers. A Python for loop that just goes through each item and then adds it to a total. It's written in Python. It's not a bulk API. It's not a fast API. It's operating from our perspective on every individual item, and it's certainly not fast. It's very slow. Python's built-in sum function is written in C, and it is a bulk API. So in that sense, it's a vectorized API. But it's not a fast API because it calls back into Python for every item. Now, if you want an API that is both a bulk API and a fast API, the vectorized API you want is NumPy's sum function, because that can just bypass Python altogether, and therefore it can run very quickly. So now that we know what vectorization is and how it allows us to write and how it makes our code faster, we can think about some practical implications of what we learned. So first, if you are processing large amounts of data, try to avoid Python's built-in objects, like Python lists. Instead, you want to use something like a NumPy array, a Pandas data frame, other similar libraries, all of which will use representations of the data that can be used efficiently. So for example, if you want to process some data that's in a CSV, and the first column is some numeric data, some floats, you could use Python's built-in CSV reader and create a list of floats, but then processing that data will be slow later on. So instead, you're much better off loading the data in Pandas, and then you will have a data frame, which underneath the hood is a NumPy array, which means if, for example, you calculate the mean or the sum, or do other sort of operations on it, you'll be able to use fast APIs. If your data isn't in a representation that is you're able to work on efficiently, then you will not be able to do anything fast. So you want to make sure your data is stored from the start in a fast representation, like a NumPy array or something equivalent. You don't want to iterate over things in Python. Just because something is a NumPy array doesn't mean a Python for loop will be slow, will be fast. Doing a Python for loop over a NumPy array will still be very slow. So you don't want to use Python for loops. You don't want to use list comprehensions. You don't want to use a map. basically anything that iterates over an object in Python is going to be slow because it is using Python APIs, it's calling back into Python as Python object conversion overhead for every item you iterate over. So instead of iterating in Python, you want to use vectorized APIs to do the iteration internally in a fast language. You also want to avoid calling back into Python. And this can be a little bit harder to spot. So let's say we have a data frame. Think of it, if you're not familiar, you can think of it as a spreadsheet with columns. And so we're looking at one of the columns in the spreadsheet. It's a Pandas data frame. We have a column called counts, and we want to get the absolute counts. The counts might be negative or positive. We want to convert them into positive numbers. So we're using numpy.apps, so that's good. It should be a nice fast function. But this operation is not going to be fast necessarily, because the map function accepts a generic Python callable. And so it's going to take, depending on the situation, it might be taking individual items and calling them on generic Python objects one by one by one. And the specific details might depend on a specific APIs you're using, but anytime you're looking at the situation where it might be calling things item by item, even if you pass in a fast function, if it's calling that fast function a million times, that's not fast anymore. Calling a Python API for every item is going to be slow, even if the underlying function is fast. So instead, you want to use a style of calls where you're passing in you know that you're operating on the whole column or a whole array, and you're passing the whole thing at once into the vectorized API, in this case, apps. Apps can operate on both individual items and on whole arrays. And so you want to make sure you're using it in the mode where it's operating on the whole array, because that way it can actually bypass Python and do the iteration itself, and not have to have lots of Python objects fed to it. But if you're doing things item by item, it will be slow. So you want to make sure, even if you're using a fast function, that it's not being called for every single item in your array, because then you're back into the world of slowness. So to summarize, if you want to write fast data processing code, don't use built-in Python objects like lists. Instead, use something like a NumPy array. Don't iterate in Python. Rely on APIs that will do the iteration for you in a fast language. Don't call back into Python for every item, because then you undo all the benefits you have from running fast code. And instead, use bulk, fast, vectorized APIs that operate on NumPy arrays or Panda columns or the like. So that's my talk. You can find the slides at this address. You can email me. I'm on Mastodon. And I should have some time for some questions now.
Yeah, thank you very much. If everyone's still processing, they're welcome to head to the Discord. Are you on the Discord yourself?
I will be on the Discord in the next 5 minutes, but since we have a few minutes, I can also answer questions here. People put them in the comments. And after that, I'll switch to the Discord.
All right. Oh, at least have a couple of comments. Thank you. Super interesting talk from Glenn. It really gives me something to think about while coding.
Yeah, and it's very, the most, I think, a common way that people end up writing slow code is like forgetting that you shouldn't be iterating. Like you think, oh, it's a NumPy array, so it's fast. But as soon as you go to for loop, it gets slow again. So that is one of the things to be paying attention for as you code. So the question is, how do we, if you're mixing SQL, do you want to minimize Python and maximize SQL? And in general, yes. And this brings in some additional related but slightly different data issues. So unless you're using something like SQLite or DuckDB that's built into your process, your database is elsewhere. It's a different computer, or even if it's another computer, you're talking to it over protocol. And so it takes time for the data to go back and forth between the database and your Python program. And in any case, whether or not it's like embedded database or remote database, there's also the overhead of converting from the database representation of the data into Python's representation and back and forth. So if you get 1 million rows from your database, now you have to create 1 million, like you have to convert all that data into something that Python can understand. And then if you then filter it down to 10 rows, you spent all that time converting the 1 million rows into something Python understands, only to filter it. But if you could have filtered it on the database side, then by the time you need to convert it into something Python understands, you have to convert much less data, and so you have lower overhead. And there are technologies that people are working towards that might make this less of an issue, but in general, minimizing how much data you're pushing back and forth between different domains is usually a good idea, yeah.
All right. Thank you very much.
Any other questions?
Yes, sir. X study shot about avoiding list comprehensions. What alternatives do you suggest?
So the advice isn't necessarily that list comprehensions are bad. If you have a Python list with 100 items in it and you do list comprehension on it, it's slow, but only relatively. Like you have 100 items, you're iterating over 100 items. In the big scheme of things, it doesn't matter. The issue is when you have very large amounts of data. If you have 30 million entries, then 100 billion entries, like the larger the data, the more this overhead of Python adds up. And so once you're dealing with large amounts of data, anything involving Python iteration, it becomes a problem. So for small data, you don't think about it, like list comprehension is fine unless you actually know there's a bottleneck. For large amounts of data is when you start thinking about how do I go faster. And for large amounts of data, typically you would replace the list comprehension with some series of, for example, NumPy operations on NumPy array, because the NumPy operations can operate on the whole array at once and bypass all the Python overhead. So instead of iterating yourself, you use functions that internally are iterating. So if you think about NumPy.sum, right? NumPy.sum is iterating over all the items in the array, but it's doing it internally in a fast language and on an efficient representation. And so anytime you're driving the iteration, you're doing a for loop using a list comprehension, using an inefficient representation. If you allow your NumPy or Pandas to drive the iteration and it doesn't call back into Python, it'll be much faster. And you want that once your data is of a sufficiently large scale. For a small, like for day-to-day, I have 100 items in a list comprehensions are fine.